Hello. Hi. Good evening. Hi, Niranjan. Am I audible?
Yes, sir. Good evening, sir.
Good evening. Good evening. So let's start the session with week 6 assignment. Is there any doubt from last week?
No, sir.
Okay, great. So how are you?
अच्छा है, sir.
Achha. So what are you doing right now? Means as a degree or job?
With job, sir. With
Okay.
job.
Okay.
Working
Nice.
professional, sir.
Working professional in core electrical or electronics?
Triple E, sir.
Triple E. Okay, nice.
Yes, sir.
Thanks for sharing. Yeah.
Thank you, sir.
Okay, so this week we are going to cover current transformer and potential transformer. Okay, so basically they are major voltages and currents as it indicates potential transformer. It measures voltages, AC voltages, and transformer measures current. Right, but there are some limitations as well because these instruments have rating of up to maximum 10 to 100 volt, right? And we may have high voltage or high current. So how to utilize these kind of instruments at high current and high voltage levels? So for that we have transformer. So you might have studied that transformer has one feature of a step up and a step down. So in
Yes, sir.
whatever manner you want to use a step up, if when your voltage will be a step up, it means your current is going to a step down. So their current transformer will be used, right? And in the step down case, voltage will be reduced from, let's say, from 10 kV to 10 volt. So the number of turns will be on the secondary side should be 1000, or so rather on primary side should be 1000, so that 10 kV voltage you could scale it to 10 volt. So for that you need those kind of turns, right? So let us start with a question. Okay, so the question is, to reduce the ratio error of current transformer, what should happen to its magnetizing current? Okay, so there are kinds of errors in current transformer. One is ratio error and other is phase error, right? You might have gone through the
Yes.
lecture. So the ratio error is basically whatever you are feeding from the input side to the transformer and whatever you are getting on the output side. So generally, let's suppose you have this kind of transformer, okay, N1, N2. So this is I1, this is I2, okay. So if this kind of transformer is there, so what we expect that I1 by I2 should be equal to what? N2 by N1, isn't it?
Right, sir.
Yeah, to just balance the MMF or power balancing equation. From the power balancing equation, you will get this kind of expression.
Yes,
But
sir.
it is not true in practical transformer. Why so?
Voltage drop, sir. Maybe voltage drop or losses.
Exactly, voltage drop across the series branches, but again, voltage drop would not harm any level of currents in the circuit. Rather, or unless current has some other path to get diverted, right? So this primary or secondary will have no load impedances, right? Core loss resistance and magnetizing inductance. So here I naught will flow, isn't it?
Yes, sir.
So no load current, or current that flows in the core loss branch and magnetizing branch, that is going to cause you an error. So now what will happen, that I1 plus I naught is equal to I2 dash. What is I2 dash here?
Secondary current, sir.
Secondary current referred to the primary side, right?
Yes,
So
sir.
I2 dash is nothing but it's I2 into N2 by N1. Okay, so this is the current I2 dash. So ideally, I1 should be equal to I2 dash from this expression, isn't it? Here I1 is equal to I2 dash. But because of shunt branch impedances, they are not going to be equal. And because of that, this error of ratio, which we are seeing right now, I1 by I2 is not equal to N2 by N1. It is not equal, right?
Yes, sir.
Exactly. So uh, this error is, it is going to give you approximate value. It is the instrument you are going to connect to measure voltage, that will be approximate. That will not be exactly what you are going to measure. So, and further, because this is the ratio error, and how could we minimize this ratio error? That was our basic question, right? To reduce the ratio error of CT, what should happen to its magnetizing current? So how can we minimize this ratio error? So all of them are linked, basically.
Yes, sir.
Yes,
R0 or H0 should be high, sir.
exactly. Yeah. So the core loss resistance and magnetizing inductance should be very high. Okay. So let's get back to the question. So in question, it was like magnetizing current. What should happen to magnetizing current? So there were three options. It should be either very high or very low or equal to the secondary side of low current. So we have three options: very high, very low, or magnetizing current should be I2 is equal to I2.
Very
Or
low,
that,
sir.
yeah, exactly. So very low would be correct here. So that was one of the questions. Okay.
Yes,
And
sir.
that was related to ratio error. Now, let's get back to another question. That is again theoretical question, because in this week's assignment there are more theoretical questions rather than numerical. So important here to it is important here to learn the concepts behind them so that you could solve them. Uh, yeah. So another question is, a primary side of voltage transformer or potential transformer. is connected to high voltage. Okay. And secondary side is connected to voltmeter. Okay. We want to change the voltmeter on the secondary side while the primary side is still live, which means primary side voltage is still on, and we want to change the potential transformer. What is the correct way of doing this process? You cannot disconnect your primary side voltage, okay? But you want to change, voltmeter on the secondary side. So what to do? Hmm?
पैरेलल में कर सकते हैं सर, उसके बाद इसको चेंज कर सकते हैं कनेक्ट करके,
Exactly, हाँ. So
या
to
फिर उसको रिमूव करके उसको कनेक्ट भी कर सकते हैं. पीटी है ना सर?
yes. So basically ये ओपन सर्किट होने जा रहा है, राइट?
तो पीटी को तो ओपन सर्किट कर सकते हैं ना सर,
कर
केवल
सकते
शॉर्ट
हैं,
सर्किट नहीं कर
exactly.
सकते हैं.
हाँ हाँ, राइट. सो दोनों तरीका है, राइट? कनेक्ट द न्यू वोल्ट मीटर इन पैरेलल to the old voltmeter first and then remove the old voltmeter, right? So in lectures you might have seen what to do here. You just connect a new voltmeter in parallel to old voltmeter. Okay, and this is the first process. So this we have to do first. Then what we can do, we can remove the old voltmeter. Okay, and you can, you know, connect the new voltmeter as well. So anyway you are fine, you could do, because there is no problem in open circuiting the secondary side of potential transformer. You cannot do this process with current transformer, right? So
यस सर.
yeah, so yeah, correct. So now, as we talked about current transformer, so again, I'm providing the condition here for current transformer. So primary side of CT is connected with high current line. Okay, and secondary side is connected to an ammeter. Okay, now again we want to change the ammeter on secondary side while the primary side is still live. Okay, so to change the ammeter on secondary side, what we can do? What we can do? Here, can we remove the old ammeter first and then connect the new ammeter to the secondary side of the current transformer?
नो सर.
No, that is not an option. So we have only one option, that is we have to connect new ammeter in parallel with old ammeter. Okay, and then this is the first step, and then remove the old ammeter. Okay, So these are the processes which we have to follow for connecting different voltmeters and ammeters. So these kind of theoretical based questions are put in assignment 6. So you could just solve it by from these logics. Now,
Yes.
the next question is, while measuring a high voltage using a potential transformer and moving iron voltmeter, which of the following may cause measurement error? So let me write the statement. While measuring a high voltage PT, okay, sorry, using a PT and a moving iron voltmeter, which of the following may cause measurement errors? So what kind of errors in potential transformer or voltmeter?
Ratio error and phase error, sir.
Exactly, ratio errors and phase errors. So what will cause measurement error?
सर कुछ आज गड़बड़ है क्या सर? स्क्रीन मतलब जो आप लिख रहे हैं वो दिख नहीं रहा है।
कुछ भी नहीं दिख रहा है क्या?
ना नहीं दिख रहा है, पूरा कुछ मिसिंग है क्या?
ओ, कब से? स्टार्टिंग से क्या?
यस सर।
Oh, shit. Okay. You should have told. Sorry.
मेरे को लगा कि हो सकता है कुछ प्रॉब्लम है इसलिए मैंने बोला कि
No. Thanks for pointing it out. Actually, I didn't know.
मेरे को लगा मेरे साइड में दिक्कत है क्या, इसीलिए मैं तभी से कोशिश कर रहा था, कुछ प्रॉब्लम तो नहीं है मेरे तरफ से।
नहीं, बोलना चाहिए था। मैं कब से लिख ही रहा हूँ।
हाँ वो तो मैं देख रहा था सर।
So, I hope it is fine now.
यस सर।
Okay, great. Thanks. So, while measuring a high voltage using a potential transformer and a moving iron voltmeter, which of the following may cause measurement error? So, let me show you the slides which I have just. So this was the first question, right? Okay, and this and all I have written. So anyway, I'm going to share the slides as well, so there should not be issue. Okay, so yeah, so coming back to the question, while measuring a high voltage using a PT and a MI voltmeter, which of the following may cause measurement error? So of course, we have two errors, right? Ratio error and phase error. All right. So do you know what is phase error? Niranjan?
Phase error means sir, both are not same in same phase sir, out of phase.
Yes. So basically, I1 plus I0 is equal to I2 dash, right? So
Right.
I1 will have some angle, let's say theta 1 plus, sorry, plus I0 will have some other angle, theta 2, and this I2 dash will have some other theta 3. Now, ideally, what should happen? Ideally, theta 1 should be equal to theta 3, isn't it? But because of this no load current, those angles are not going to be same. Because if you take phasor, right? So if you take phasor, this is your I1, let's suppose, and I2 will, sorry, I0 will still be lagging because I0 is in highly inductive nature. So ideally it should be 90-degree lagging if your core loss is zero in ideal transformer. But here in practical transformer, it is not the case. So I0 is like this. Now your resultant I2 will be like this. Okay. So there is phase angle introduced in I1 and I2 dash. Otherwise, ideally, what should have happened?
Both are phase angle between zeros.
Yeah, both should have been same. This is I. Okay, so this is the phase error. But because of phase error, could we experience any measurement error? Because if you are going to measure, you are not going to get any angle from the measurement, right? You will only get magnitude, but angle you could calculate, separately. Okay. So that is why the correct option for this question is ratio error, right?
Yes, sir.
Okay. So let us move on to the next part. Yeah. So next part is mostly related to flip-flops and latches. Okay. But before that, let us solve questions based on the instruments. Then we will enter into electronics instruments where latches and flip-flops are explained, right? So, yeah. So the next question is, we have to measure AC voltage of 1000 volt. Okay. We have voltmeter of range 0 to 20 volt. Okay. So with 20 volt of voltmeter, we have to measure 1000 volt. Now this voltmeter have internal resistance that is equal to 1000 ohm. Okay. Now we'll have to use a suitable PT to change the range of our voltmeter, right? So basically, potential transformer is what they are doing. They are stepping down the voltage, right? So or scale up the voltage
Yes,
on
sir.
the other hand. So we'll have to use a potential transformer of what ratio? N1 N2 N1 is to N2. That ratio
50
should
by
be how
1.
much?
50 by
Sorry,
1, sir.
50 by 1. Yeah,
50 by 1.
50 by 1. Exactly. Basically, it is nothing but 1000 by 20, right?
Yes, sir.
1000 is to 20. So if you divide it, it will be 50 by 1. But if in the exam, if you will be asked the number of turns ratio, then you mention 1000 into 20. Okay. Because what happens,
Yes, sir.
uh, division, you could do that because of mathematics, but it is not exact mathematics. So in instrument, the exact number of turns will be 1020. So that will not be 50 and 1. Okay. Because of, of course, EMF and flux and all of them should be maintained. So that is why the number of turns should not get, tempered.
सर
So
ये जो
please take care. हाँ,
1000 बाई 20 दिया हुआ है, ये तो आपका वोल्टेज दिया हुआ है सर, तो मतलब
हाँ,
नंबर ऑफ टर्न्स तो इंक्रीज भी कर सकता है सर,
इंक्रीज कर
ये भी तो
सकता है, बट
एग्जैक्ट तो
नंबर
नहीं
ऑफ
होगा सर.
एग्जैक्टली, बट नंबर ऑफ टर्न्स इंक्रीज करने से क्या होगा? इफ you have n right? If you increase N, then what will happen? Your inductance will increase. Then your
Right, sir.
magnetic flux in the core, that will change. Magnetic core will be more saturated. Or if you reduce the number of turns, your saturation will also reduce. Flux density will also reduce. So whatever the power we were able to achieve at 1000:20 number of turns, you will not achieve with 50:1 number of turns. Because in electrical machines or electromagnetic devices, power is proportional to magnetic flux as well as electrical current. So we'll have to take care of both of them. Got it?
Yes, sir.
Okay. Okay, so we have to calculate power that is consumed by potential transformer while measuring 1000 volts. So power consumed by potential transformer, let me. We have to find out this. Okay, so how to find out? So potential transformer will obviously be connected on the secondary side, right? On 20. So V of potential transformer will be, or secondary side will be 20 volt. And resistance is given. Resistance of potential transformer is given, right? So we could
V square by R, sir.
V square by
V
R,
square by
exactly.
R.
V square by R. So 20 square by 1000. So it is 0.4 watt. So yeah, very small losses are there. So, but still, this much loss will be there if you are going to measure 1000 volt of AC voltage with 20 volt of voltmeter, right? This much loss you have to consider into account when you are going to supply. So that loss is basically what? That is your error. So whatever you have provided input, that you are not going on output. So that much loss is happening in between. So that is indirectly an error. Okay. Now we have to find out equivalent resistance from the primary of the potential transformer. So we have 1000 ohm on the secondary side. So what will be the equivalent resistance from the primary side? So R2 is 1000 ohm. We need to find R2 dash. So R2 dash will be, since it is being referred on the primary side, so that will come on the numerator. And from the side it is getting referred, that will come on denominator. And you'll have to take the square. Yeah. So sorry, here it should be R2 only. Now it is 1000 into N1 is 1000, right? N2 is 20 square. So how much it will come out to be? Thousand into 50 square. Yeah, so it is 25 kilo, 2.5 mega ohm. So from the input side, if you will see, it will be 2.5 mega ohm. Okay, any doubt in this?
No, sir.
Okay, great. Now, again, this is with potential transformer. Now with current transformer. We again need to measure thousand. Okay, and ammeter we have of range 0 to 10 ampere. Okay, and R internal of a meter is how much? That is again 10 ohm. Now we need to calculate the power loss, okay, while measuring 1000 ampere current. So first thing first, number of turns ratio, N1 by N2. How much? 1000 by, sorry,
100 to 10 by 10 by
yeah,
1000.
10 by 100, 10 by 1000. Okay. So this is the first thing you have to do. Now, when 1000 ampere is flowing on the primary side, 10 ampere will be flowing on the secondary side, and a meter is connected on the secondary side only. And we have been given with the of 10 ohm. So power loss I2 square R 10 square into R. So it will come out to be 1000 watt, isn't it? So, you know, in a meter, it is providing significantly as compared to voltmeter. Here, it is getting very low, not very efficient. Compensating coils should be used there in these much losses, because while measuring itself, if you are going to watt, then it's a serious issue, right?
Yes, sir.
Now, how? Yeah, should be equivalent resistance from the primary side R2 dash watt. So we are given with R2 into again N1 by N2 square. So R2 is 10, N1 by N2 is 10 by 1000 square. So 10 by 100 square. So it is 1 milli ohm.
Right, sir.
1 milli, yeah, so 1 milli ohm resistance. So that is why very high current is flowing and input resistance is very low. So of course losses will be high. Okay. Any doubt about this?
No, sir.
Okay. I guess one doubt will be there regarding ballistic galvanometers, isn't it? So what is ballistic galvanometer? So two questions will be there in the assignment based on ballistic galvanometer. So basically it is used here a concept of magnetic flux and electrical current both will be combined, so you could relate both of them, that how they are related, interdependent. So it can measure the total charge flown during an impulse current. So what we basically do, uh, we disconnect the switch. Okay, we disconnect the switch and we calculate the change in flux. And once we know the change in flux, we can know the EMF. And once we have EMF, we can get current as well, right? So let me show you. So this kind of arrangement is made. This is the core of the transformer. Okay. This kind of core is there. Okay. Now, similarly, on the secondary side, again we have galvanometer. Okay, this is the secondary coil. This is first primary coil. Okay, here N1, N2, I1, and again here I2. Now, flux, whatever Ni is, so initially they will be initially the switch would be connected. Initially the switch would be connected, and because of Ni MMF, right, in one I1 MMF, one flux would be established in the core, and because of N2 I2 also, if you take if you rotate your thumb, it will give you flux in this direction. Okay, but uh, as per the Lenz law, the you know both the flux should oppose each other, and the change of flux linkage is equal to EMF. Okay, so when we are disconnecting, it means we are intentionally creating change in the circuit. So initially the current was I1, and now the current will be 0. So current changes from I1 to 0. And let us suppose that initially when the switch was connected, the phi flux was flowing in the core. Phi was in the core. So how much will be the flux linkage on the secondary side? Phi is flux, so flux linkage would be how much? It will be multiplied with number of turns, isn't it? N2 into phi. So the change in flux linkage will be, and after disconnecting the switch, flux would be 0 because there is no supply. So for some momentarily, some flux will be there, but after the point of time, because of magnetic property, they will decline to 0. So final flux linkage after switch is disconnected, final flux linkage is 0. So the change in flux linkage, so del psi, is N2 phi minus 0 is nothing but N2 phi. Okay. Now phi is equal to B into A, magnetic flux density into area. So the change in flux linkage will nothing but BA into N2. Okay. And in questions, in assignment question, you will be asked to calculate magnetic flux density. Okay. And permeability of the core. So here, give your attention, please. Now, how to proceed? So from this point, you have the change in flux linkage. If you divide it by delta T, you will get the back EMF, right? You will get back EMF, okay? And this back EMF will be equal to current by R. Because of back EMF, there will be some current. in the secondary turns, on the secondary side, there will be some back EMF, right? E2. Because of this back EMF, some current can flow in this direction, or depending on the arrangement of the coil. Okay. So that so now we can equate BAN2 is equal to I delta T into divided by R. And I delta T is nothing but charge by resistance. And our purpose was to calculate magnetic flux density, that is nothing but Q by R AN2. Sorry, Q into R, right? I delta T. Q. Yeah, yeah. Okay, the mess is here. It should not be I by R, it should be IR. IR. Equal to IR. Now B is equal to I delta T into R divided by A into. Okay, so it will lead to QR by A into. So this is very important expression of magnetic flux density in ballistic galvanometer, which you will be asked quite frequently. So here Q is nothing but charge, R is resistance, A is your area, and N2 is the secondary number of turns. Okay. So let's get back to the question, what was asked in the question. So in the question, it is said all the parameters I am going to write of ballistic galvanometer, and N1 is equal to 50, N2 is equal to 600, okay, and cross sectional area is 2 centimeters square, and mean length of the core is 25 centimeter. Okay, let me write cross sectional area. Mean length of core. Now, charge sensitivity of ballistic galvanometer. So, charge sensitivity is given to calculate the quantity of charge indirectly. Sensitivity of ballistic. Which is denoted by S at 2 centimeter by microcoulomb. Okay. Now, total resistance of the secondary circuit on galvanometer side. So, on this side, right? The circuit resistance on secondary side is given. R2 is provided as 4500 ohm. Okay. And I1 is also provided before the switch was opened. I1 is 0.4 ampere. Now, when the switch is opened and galvanometer shows an oscillation of 8.5 centimeter amplitude. So galvanometer 8.5 centimeter. right? So there are a lot of data to process. Okay, so do not no need to get scared of this much data. We need to calculate magnetic flux density in the core. So we just calculated the expression of magnetic flux density with the help of change in flux linkage. So what was that expression? We have calculated it here, QR by AN2. So we are going to write QR by AN2. Okay. Out of 4 unknown parameters, how many do we know? So we know R. R is nothing but 4500. Area is given 2 centimeters square. N2 is given 600. Q is not given directly, but Q we can, or charge we can calculate from the units. If you do not know charge and sensitivity, no need to worry, just focus on the units. So it will be this oscillation deflection, that is 8.5 centimeter. If you take galvanometer oscillation divided by charge sensitivity, you'll get the quantity of charge in on the secondary side. So that will be equal to 8.5 centimeter divided by sensitivity 2 centimeter into 10 raised to power minus 6. Is it? Yes. So how much it will come out to be? Let me calculate. So it is 4.25 into 10 raised, they will cancel out. So 4.25 microcoulomb. So that much charge is present in the circuit. Now we need to calculate magnetic flux density. So we now know all the parameters. It is also 4.25 microcoulomb. So we just need to compile. So how much it will come out to be? It is coming out to be 0.1593 Tesla, which is quite low, but fine. Okay. So this much magnetic flux density will be there in the core of this ballistic galvanometer, right? Any doubt in this part, Niranjan?
No, no, sir.
Great. The sec the sec the second part is we need to calculate permeability. Mu, which is basically mu naught mu r. So how much will be permeability of this core? How to calculate? With this much given data, I'll present the data in front of you.
बी और एच का ये रिलेशन निकाल सकते हैं
Exactly,
H.
excellent, excellent. So B is equal to mu H. Okay. B we already calculated 0.159. Isn't it? H we don't know yet, but we are going to figure it out. So H, what is the expression of H? The unit is ampere per meter, right? So from the ampere law also, you know that H dot dl is equal to I, isn't it? Or if there are n
Yes,
number
sir.
of turns, you could multiply. So H is nothing but Ni by L. L is the mean length of the coupe. So we are just going to plug them. So mu is, sorry, not mu naught, it should be mu. So mu is equal to 0.15 divided by Ni into L. So which n we have to consider? Here in
Secondary, sir.
secondary. And current?
Current primary side, sir.
Current primary side. Why? Because in the question it is given or any other reason? Question primary side current is given.
नहीं सर, वो कोर लॉस जो होता है ना,
So actually here N1 and N2 is given and no information about losses are provided. So you could straight away assume that it is an ideal transformer. N1 by
okay,
N2 is equal to I2 by I1. Okay. So that is why it was a bit tricky question because here no matter whichever number of turns you take, current also you will have to take of the same branch or the same side. So it doesn't matter whether you take N1 I1 or N2 I2. Both will be same. Okay. Now, since in the question I1 is provided, so it is better to go ahead with N1 I1. Right? Otherwise, you could calculate I2 as well. How to calculate? Because we have all the parameters, we have charge, we have resistance, we have we can calculate EMF, that is change of flux. So we could go ahead with that process. But since it is already provided in the question, you just take the least reluctance path, isn't it? So 0.15 into mean length is given 25 centimeter. And I'm going to assume N1 I1. So N1 is 50 and I1 was 0.4 ampere. Okay. So if you calculate, you will get
1.8 million.
yeah 1.8 milliwatt Henry per meter, isn't it?
Meter.
Henry per meter. Okay. This Henry per meter is coming from which expression? L is equal to mu n square A by L. So from this is inductance and this is length. So from this expression, if you calculate, you will get this unit of mu, this mu. So this is Henry. This is corresponding to Henry. This is corresponding to Henry. This is corresponding to meter. Okay. and this is unitless n square. So mu and zipper, isn't it?
Yes, sir.
Yeah. Okay, so we are done with all the assignment questions of potential meter, potentiometer, sorry, potential transformer and current transformer. Okay. Now we are going to see or enter into electronic instruments where latches and flip-flops are given. Okay. So you might have studied it in different subjects or earlier, but it is important to revisit because they are going to be used in further assignments also. So for that purpose, let us start with SR flip-flop. So the SR flip-flop is given in the question, and you need to identify what kind of characteristics of output will be there. So how a SR flip-flop could be designed. So two NOR gates, okay, they will have one input which is considered as S, isn't it? And other input will be connected to the output of the other NOR gate, and here the second, which is considered as R. Okay, and both the outputs are complemented to each other, Q bar. Okay, and this is SR flip-flop. Now we have to find out which terminal is reset input and which terminal is set input. Okay, so like in which case you are going to get output is equal to 1, right? You want to achieve output is equal to 1 or Q is equal to 1. So in that case, which terminal you should keep reset and which terminal you should keep set? So basically there are two options only. Either you keep this one as 1, this one as 1, and keep it second one 0, right? So this one will come out to be, you know, NOR gate. So one and anything of OR will be 1 and NOR of that will be 0. I hope you got this portion, right? If you are feeding 1 here,
Yes, sir.
no matter anything you put X or anything, your output is going to be 0. Similarly,
Yes, sir.
on the second hand side, if this 0 is here, this 0 is coming out here, 0 and 0. So OR of 0 and 0 is 0 and NOR of 0, 0, 1.
1.
So your key Q bar is getting equal to 1 in this case. So S is equal to 1. This we are calling S, this we are calling R. And R is equal to 0 will not lead to Q is equal to 1. It is going to provide Q is equal to 0. So here Q is 0. So that will not be the correct option, isn't it? Now let's go ahead with the other option. Yeah. So now we are going to feed 0 on S, right? The opposite of the earlier. We are going to feed 0 here, 1 here. If 0 is getting fed here, we don't know whatever will come out, but we can make sure on the R hand side that if 1 is here, anything, if you null with 1, that is going to produce 0, and this 0 will come out here, and this 0 of null will give you 1. So here now Q is 1 and Q bar is 0. So that will work, right? So that is what was asked in the question. So you could keep S is equal to 0 and R is equal to 1 to get Q is equal to 4. So that will be your answer to this question. Any doubt in SR flip-flop?
No, sir.
Okay, so SR stands for what? S stands for set and R stands for reset. Okay. But you could not keep S is equal to 1 and R is equal to 1, because what will happen? Let's see. That was in the lecture. It was mentioned to explore yourself. So let us keep S is equal to 1 and R is equal to 1. What will happen here? So 1 into NOR of anything will give you 0, isn't it? And here this 0 will come out, and again 1 and NOR of anything will give you 0. Then this 0 will come out here, then again it will be 0. So both the output will be 0. That is why this input is not allowed. Q and Q bar both will be 0. So that could not happen. We do not want any such output in which complement of the output should also be 0, and they are going to be always 0. So that is why it is not allowed. Okay, I hope you understand, because NOR of anything with 1 is going to give you 0. Again, NOR of this NOR gate will again provide 0. So it will be always 0. Both of them will always be 0. So there is no use of such inputs. Okay. Now with the SR flip-flop, can we make D flip-flop? So yeah, so D flip-flop could be made with SR flip-flop. Let us design one D flip-flop with SR flip-flop. So we just need to provide one AND gate with toggle. So let me show you. So this was okay. This is SR flip-flop. These two are SR flip-flop. Okay. Now this input will be connected to one AND gate. So it will be like this AND gate will again have one input. Okay. And this will be a clock. Whenever you provide clock input, your output will change. So that is the importance of clock in flip-flops. And this is D, and that is connected with one NOT gate. with one inverter to the other AND gate, right? So it was S, it was R, it is like that. Okay. Now, when when this clock is provided, then only your output Q and Q bar are going to act. Otherwise, they will remain in the previous state. Whatever the state is maintained there until you give clock pulse, your output will be similar to the whatever state it was before. Okay. Now, if you provide clock, okay, and S and R, okay, if your clock is 1 and if your D is, if your D is there, S and R are there. Okay. So this S is nothing but D. If clock is 1, right? If clock is 1, S is D and R is D bar, isn't it? I hope it is fine till now. And when D is equal to 1, what will happen? S will be equal to 1 and R will be equal to 0. So when your D is equal to 1, S will be equal to 1 and R will be equal to 0. And we know this 1 and NOR will give you 0 and R, this 0 and 0 will give you 1. So at that case, it will provide you output of 0. Output means Q will be 0. In another case, when D is equal to 0, when D is equal to 0, S will be equal to 0 and R will be equal to 1. In that case, what will be Q? In that case, Q will be 1. So when S will be 0 and R will be 1, in that case, Q will be 1. So what does it imply? It implies that whatever the value of D you are going to provide to this flip-flop, this D flip-flop, this is named as D flip-flop. The same will be reflected to the output of the flip-flop. Okay. So you just need to give any input here, same will be reflected to the output. So that is what happening here. If you see carefully, okay. And when your clock is 0, your Qn plus 1, the next stage will be equal to Q previous stage, right? So that is what it implies. So there are two types of triggering in the flip-flops. One is level triggering and another is edge triggering. Okay. So what are the differences? So let us see.
लास्ट वाला स्टेप सर when clock equal to 0 ये थोड़ा सा
Acha, when clock is equal to 0, Qn plus 1 is equal to Qn. That's what you are asking. Yeah.
yes sir
So yeah, so if you are not giving any clock, okay, and whatever you are giving on the input side, right, 0. So here it will be 0 always. Both of them will be, 0 and 0. Okay, here both of them will be 0. So what is the condition of when S and R both are 0? Then what will be the output? So let me explain it further. That's really a good question. You are not taking anything for granted, that is a good indication. So yeah, so this is very special case when both of the inputs are 0. Then what happens, that you have to consider whatever the q, this is the q bar and this is q, isn't it? Now I hope you are not getting confused here. This q will come here and this 0 is already there. So q and 0, so nor of q and 0, so that is going to depend on the memory, isn't it? So nor of q and 0, q and nor with 0. So q and or with 0 will be equal to q, and q and nor of 0 is equal to 0. I hope you are getting. Why I am writing q or 0 is equal to q? Because at the place of q, either it is 1 or 0, doesn't matter. Whatever the value will be placed at the place of q, that will be output. If q is equal to 1, this will be 1. If q is equal to 0, it will be 0. So that is why I am saying here q and 0, or of q and 0 is equal to q. Is it clear till this point? Or of q and 0 will be 0. Is it fine, Niranjan?
Yes, sir.
Okay. Now, nor will be what? Nor will be opposite. Q and nor of 0 will be what? Is equal to q bar. Isn't it? So this q bar is equal to q bar. Nor of q and 0 is equal to q bar, which was q bar earlier. So it means whatever the input, that is same as the output. So that is why we are calling it is holding the memory. It is not changing anything. Let us see on S nor. So here again it is 0. Okay. At S, it is S is equal to 0 and q bar is coming from here. So nor of q bar and 0, nor of q bar and 0 will be how much? Q, isn't it? Nor of q bar and 0 is q. Is there any doubt in this? In this statement, nor of q bar and 0 is equal to q. If you have, please ask, because it will be, it could be, it is confusing.
और एक बार
If it,
रिपीट कर दीजिए सर थोड़ा सा.
okay, okay. So let's make me one different SR. Okay. Okay, here it is S, here it is R, Q, Q bar. Okay, just listen carefully. S भी 0 है, R भी 0 है, ठीक है. यहाँ पे Q यहाँ पे आ रहा है, ये Q यहाँ पे आ रहा है. Q will be here. Okay, now Q and or 0. I think the symbol of or is correct, right? I have forgot. Symbol of or is correct or wrong? Anyway, let me write as operator or of q and 0 is equal to how much? q. ठीक है, q और 0 का और ऑपरेशन लगाएंगे, q आएगा. q के जगह पे 1 डाले,
Yes, sir.
0 डाले, वो उतना ही देगा. अगर q के जगह पे 1 डालेंगे तो q आएगा, q के जगह पे 0 डालेंगे, q आएगा. ठीक है, एग्रीड. नाउ
Yes, sir.
nor of q and 0 will be complement of this, isn't it? All of q and 0 का complement होगा,
Yes, sir.
which means q का complement होगा, so q बार हुआ, which means इसका आउटपुट क्या आएगा? q बार आएगा. So ये Q bar ही था and Q bar ही रह गया. It was initially Q bar and output is again Q bar. It means memory is not going to change. Memory is not getting changed. So you have the memory, whatever the initial value, whatever the Q bar n plus 1 is equal to Q bar n. Even कितने बार भी clock लगा दे, it doesn't matter. No matter how much times you trigger your clock, it is going to be same until your S and R both are 0 or both are not getting changed. ठीक है, यहाँ तक clear?
Yes, sir.
Okay. Now on ऊपर देखते हैं S पे. So S पे क्या है? यहाँ पे Q bar is coming at this node, right? So now first OR of Q bar and 0 will be what? OR of Q bar and 0 will be Q bar. Of anything
Yes, sir.
with 0 will be that much. Okay. Now NOR of Q bar and 0 will be Q bar का bar, which will be equal to Q. ठीक है, तो यहाँ पे Q आया,
Yes, sir.
अगेन Q ही रह गया. तो मेमोरी चेंज हुआ, पहले जो था प्रीवियस स्टेज पे जो था वही नेक्स्ट स्टेज पे है, वही नेक्स्ट स्टेज पे है, चेंज ही नहीं हो रहा है. इट मींस दैट
Yes,
इज
sir.
व्हाई वी कीप राइटिंग मेमोरी. इट मींस द स्टेज विल नॉट चेंज. ठीक है, आई होप इट इज क्लियर.
Yes, sir.
ओके, ग्रेट. सो वही किए हम लोग. ठीक है, एसआर में डी लगा दिए, एक एंड गेट लगा के उसको डी फ्लिप फ्लॉप बना दिए. whatever will be the input on D, that will be the output. Okay, now we will see the triggering. Okay, so let me see if any question could be solved based on this much information. Okay, so one question in the assignment is based on master slave flip flop. I hope you guys must have identified this question. Okay, but let's first finish D flip flop and then we will finish master flip flop. Okay, then you will be able to solve all the questions from the assignment week 6. I'm just going to take 1 minute break. Okay, please excuse me for 1 minute. I'm back in 1 minute.
Okay, sir.
Okay, thanks. Yeah, sorry for that. So let's get started. Yeah, so now we have to care about triggering. So there are two types of triggering. One is level triggering, other is edge triggering. Edge triggering could be done with either positive edge triggering or negative edge triggering. So let me show you the clock. Okay, so here this is the clock. This is how clock will be there with certain frequency. So it will be periodic clock frequency, 5 kilohertz, 10 kilohertz, anything you could provide as input, right? Now this is clock. Now you have another thing, that is D flip-flop. D flip-flop also you could use as input. So any random input I am going to give, okay? Any random signal could be inserted or could be supplied with D input, right? Now, if we want output, that is Q, okay? On the edge triggering, let's first discuss with edge triggering. So I want to have on negative edge triggering, which is very famous, negative edge triggering, okay? Now how my output will look like? ये अपना क्लॉक का सिग्नल है, ठीक है? ये अपना डी फ्लिप फ्लॉप का है, वो कैसा भी सिग्नल है, ठीक है? एनी रैंडम सिग्नल with signal generator, okay? So अब output, how it will look like output? So first thing is that we have to identify where the negative edge is getting triggered. So this at this point, all of these points are negative edge triggered, right? When the clock is going from 1 to 0, okay? Which means ki your output will change only at the instance of the negative edge triggered at this instance, okay? Whatever will be the input at this instance of the D, that will be is equal to Q, okay? So at this instant, we are going to map, so the D value is going to be 0, okay? So let me take another color. Okay, ठीक. So it will be 0 until this instance, until next clock is identified. अब जब ये क्लॉक ट्रिगर हो गया, उस टाइम पे भी D का वैल्यू कितना है? 0 है. Then again it will keep maintaining 0 till the next clock, okay? ये क्लॉक पे D 1 हो रहा है, तो ये आउटपुट भी 1 होगा. Why? Because Q is equal to D. As per the D flip flop, if you are providing, this is the D flip flop, let me draw. This is the input of D, this is the input of clock, this is output, okay? So whatever the signal you are going to inject in D flip flop, your Q will be equal to D into this clock, okay? Now at this edge, it is going to become 1 till the next clock edge point. So at this edge also, the the D flip flop value is 1, so it will keep maintaining 1, okay, till the next clock. Any doubt in this graph, this output graph? मैं एक बार फिर से समझा दूंगा if there is any doubt.
No, sir.
Okay, great. So this is how negative edge triggering works, okay? Now what will happen with positive edge triggering? In the same graph, I'll draw positive edge triggering. Q with positive edge triggering, okay? Okay, so this is the positive edge triggering, okay? All the black arrows. This is for negative edge. This is for positive edge. Okay. So at this instance, the value of D is 0. Okay, so it will keep maintaining 0 till the next positive edge. At this positive edge, the value of D is 1, so it will switch to 1. Okay, till the next positive edge. Again here, the value of D is 1, it will keep maintaining 1 till the next positive. Again here, the value of D is at this instant is 1, it will keep maintaining 1 till the next positive clock. Okay, so this waveform of positive edge will be something like this and negative edge will be something like this. Okay, I hope it is clear. Now the last part is level triggering. Okay, so the level triggering means at this portion is the level triggering, isn't it? So whenever there is it becomes 1, this clock becomes 1, whatever the value of the D at this instant, that will replicate the value of D. Okay, here it was not replicating, it was just capturing and it was maintaining it. Okay, now it will replicate at that clock period. So let me copy it first, otherwise it will be a bit messy. This much should I copy? Okay, so this is what our D flip-flop and clock signal looks like. Now we have some other axis. Okay, so this level is getting triggered for this period, right? For this period. Okay, I hope you understand with the terminology level triggering. Level triggering means for the period your clock is high. Okay, so for this much period your clock is high. Oh, sorry. For this much period your clock is high because clock is the first one, right? So for this much period clock is high. Yeah. So for this much period your clock is high. Now at that period, at that level, at that period, whatever the shape of the D signal, that will come out in the output as it is. Okay, for that period only. This portion will not come out, right? So only this much. Okay. So here the width is this much, but here it is smaller. Okay, so please pay attention to this detail. Okay, so this was for this clock, and for this level triggering, the shape is like this. Okay, and now for this level triggering, the shape is again like this. Okay, okay, so your output will look like something this. Any doubt in level triggering?
No.
Okay, great. Now the final thing is master slave flip flop, and after that we will solve that last question, and we are done with the week 6 assignment. Okay.
Okay, sir.
So in master slave circuit, we will have two D flip-flops cascaded with each other, and you could see the output of both the circuits. So how they will look like. Q1, okay, D1, and this is clock, and this Q1 will get fed to D2, okay, and here again another clock is there, and this clock is, you know, complement to each other. Both these clocks are complement to each other. Or rather, you know, hmm, Q2, okay, or Q also you put that, but Q2 is fine, okay. So here the output will depend on both the flip-flops. So Q2 will be equal to Q1, okay, when this clock is equal to 1, when clock is equal to 1, Q1 is equal to D1, okay. But when clock is equal to 1, then this clock will be 0 because it is inverted, right? So Q2 will be 0, okay. I hope you got it. And when clock will be 0, Q1 will be 0, okay. Q1 will be 0 and Q2 will be, then in second case clock, this clock will become 1, but since D2 is equal to 0, so Q2 also will be 0. So in both the cases Q2 is 0, okay. So is there any point of using such kind of flip-flops? In all the cases, if you are going to get output as 0, then there is no point of using such flip-flop. It means we have done something wrong, or we have to modify this flip-flop, right? So what modification we could do? We could do a slight modification here on the clock signals, okay. So let me, so give one inverted clock to the first flip-flop, okay, and give one more inverted clock to the second flip-flop. Now what will happen in the second case with two inverted switches, or with two inverted gates? Now your output will be 1 for some amount of time. So when clock is 1, then this clock is 1, then this will be 0, and 0 will be there, then Q is equal to previous, right? Q1 will be equal to previous. If clock is not there, then your Q1, Qn plus 1, okay, Q1 is equal to Q bar or Q dash, That is just to identify that it is previous state, or let me write it as Qn minus 1. Okay, it will be previous stage. Okay, now in second, if clock is 0 here, it will be 1 here. Okay, and since Q1 is Qn minus 1, Qn minus 1 into 1, it means what when clock is 1, whatever is given as D2, that will be exact is equal to Q2. So Q2 will be Qn minus 1. Okay, so when clock is equal to 1, then Q1 is also Qn minus 1, Q2 is also Qn minus 1. It means the final output is equal to the previous stage or a state. Previous state, it means it is holding the memory. Okay, when clock is equal to 1. Now, in the case when clock is, what will happen is equal to 0, it will appear here as 1. Now Q1 is equal to D1. Okay, and this clock will, and whenever clock is 0, it will hold memory or whatever is coming here. So Q2 will be equal to D2, which is equal to D1. Okay, or Q2 is equal to memory. What will be the output? Q2 will be equal to memory or Q2 will be equal to D1? In this case, when this clock is 0, Q2 will be equal to D2, which is equal to D1, or Q2 will be memory. What do you recommend?
memory, sir.
Memory, exactly, memory. So Q2 will be equal to memory. Okay. So in both cases, it is going to provide you memory. Now, how they will change, that is another thing, right? What is happening that once you are providing as clock is equal to 0, then your Q1 could change. Whatever you are going to provide here input, that Q1 could change, but Q2 will be providing the only memory, right? So that is why Q2 is changed at the rising edge of only, at the rising edge of the clock, but Q is not changed. So that is why let us now draw one waveform so that to get better understanding of it. So since both the clocks are complement of each other, so clock 1, let's suppose, okay, that this, then like this, like this, okay. The second will be complement to each other. Okay, so this is the clock. This is clock to the first D flip flop, D1. This is the clock to D2. Okay. Now, when D1 is positive and D2 is negative, okay, in that case, what will happen if D1 is positive and D2 is negative? Means this clock is getting here. Yeah, see that flip-flop, right? So D1 is positive and clock is 0. The second clock is 0, which means this condition. D1 is positive, means clock is 1, right? And whatever the Q1, so Q1 will be is equal to memory, Q1 will be equal to Qn minus 1 at this stage. Okay. Please relate with the D flip flop. When clock is equal to 1, here it is going to be 0 and Q1 will be equal to memory, right? When Q1 is equal to memory, then Q2 will also be equal to memory, right?
Memory.
Yeah. So Q2 will also be equal to memory. So Qn minus 1. So this one is Q1 and this one is Q2. I am writing in this fashion. Okay. So please do not get confused. Now, when the clock of D1 is 0 and clock of D2 is 1, okay, in that condition, what will happen? In that condition, clock of D1 is 0, it means it is going to be 1, isn't it? 0, it is going to be 1. Okay, and at that case, Q1 will be D. In this scenario, Q1 will be D and Q2 will be what? At this scenario, Q2 will be what? D1 is 0, flip-flop 1 is 0, and flip-flop 2 is on. At that condition, both will be the Q1 is D and Q2 will be Qn minus 1. The previous, right? I hope you are getting it. So there are only these two possibilities, and it will keep repeating n minus 1, n minus 1, D, Qn minus 1. यही repeat होता रहेगा, right?
Okay, sir.
Okay. So this is how edge triggered master slave circuit will work. Okay. So they are changing at each edges. Okay, they are not level triggered, they are edge triggered. So now there are many possibilities of connecting this NOT gates and all. Okay, so we should not, you could explore it by changing all the gates, NOT gates and all, but the output will be similar. Okay, so let us get back to the quiz question. So in quiz question, master slave flip-flop is shown and it is being asked that which kind of flip-flop is it? So master slave flip-flop, master slave flip-flop. It works on as a which flip-flop? Level triggered flip-flop, D flip-flop, negative edge triggered D flip-flop, or positive edge triggered D flip-flop. So you have to select the correct answer. Okay. So what did you observe from all these concepts? From this figure only you could observe the answer to that question. Just let me know and that is all.
एज होगा सर।
Age hoga, that is for sure age hoga from this waveform, because this D is coming. You observe carefully the value when it is going to change, when D will come in the picture, and that is coming at ages only. But whether at negative age or positive age, because the circuit is this one, right? In the question, if you see, circuit is this one. So on the negative age or positive age?
I think it's negative edge.
On the negative age of which? This, whatever, what about the value of clock? 0 or 1? Hmm? So see, whatever the clock is going to, you know, see carefully this master slave flip flop. Whatever the clock is going to the second flip flop, okay, this flip flop, whatever the clock is coming here, the same is getting as input. जो भी यहाँ पे क्लॉक का सिग्नल है 0, वही इनपुट भी है 0, राइट? एंड सेकेंड क्लॉक वैरी कर रहा है यहाँ पे, चेंज हो रहा है, डी कहाँ से स्टार्ट हो रहा है? यहाँ से, isn't it? Corresponding to D2. So is this falling or rising?
राइजिंग।
Rising, which means which option?
पॉजिटिव।
Positive edge triggered. Okay.
पॉजिटिव सर।
Yeah. So this is a bit confusing. So observe carefully, right? So whatever the clock is provided to second flip flop, that is the actual clock. Okay. So that is why we have to relate it with second flip flop. That is second D flip flop. So it is happening at a rising clock, right? So hence it is positive triggered flip flop. Okay.
ओके।
Any doubt in this? One last part. Yeah, frequency calculation. Yeah. So basically, there is one expression. Okay. We have a 16 hertz. Let me put it this way: 16 kilohertz clock frequency. Okay. And we have to get 2 kilohertz as a output. So this is clock frequency and output frequency is 2 kilohertz required. So in the question it is asked that how many T flip-flops are required using binary ripple counter. So how many flip-flops required using binary counter. Binary counter. Just a second. Huh? Sorry about that. So we were, yeah. So how many flip-flops required using binary ripple counter? Okay. So I hope you must have gone through the lectures. Okay. In the lectures, it was explained that how do we, reduce the frequency as we keep increasing the number of flip-flops, right? So binary ripple counter basically, uh, you know, if you have as input 16 kilohertz, and if you are going to use one binary counter, then your frequency will be come to 16 by 2, that will be 8 kilohertz. Okay, then further if you go there, it will further go after. But in binary ripple counter, there are certain limitations that you could go up to counting value of 9, right? At 10 it will again reset. So the time period you will have to calculate accordingly, right? So for that, we'll have to check when the output is becoming 10. Basically, that is 1010, right? If we have 4 flip-flops and we are going to have 1010, what will be this value? 100, it will be 8, right? 1001, it will be 9. 1010, it will be 10. So it will not show you 10, instead it will reset to 0. Okay, so there are total 10 stages where you will have binary ripple counter, isn't it? And there is one expression as well. uh, Actually I could explain it in great detail, but because of very less time is available, so I am providing you the expression for now. In the next session we could learn it in great detail if you want. So the expression is here, log of 2 divided by how much the frequency as input and how much is the frequency of output. So 16 kilohertz divided by 2 kilohertz. Okay, so whatever the output you will get, that will be the value, log to the base 2. Okay, and 16 kilohertz divided by 2 kilohertz. And this much binary ripple counters will be used, or this much T flip-flops are required to generate 16 kilohertz to 2 kilohertz as output. Okay, so basically we use as many stages of flip-flops that are going to reduce your frequency. Because why they are going to reduce the frequency of flip-flops or at the output? Because the second flip-flops, until they are synchronous, if and most of these ripple counters are asynchronous, so the second flip-flop will be waiting for the pulses that will come from the first output of the first flip-flop. And further, the third flip-flop will be waiting for the output of the second flip-flop. So all of them will be in cascaded, and the time period of the first flip-flop is not equal to the time period of the entire combination. So that is why this much time it takes, right? So that's the logic behind it. And you could also, count it. You could just uh, write a truth table with memory and all the inputs of the counter, and you could also identify it there from there. Okay, so that is how you could uh, and in T flip-flop, actually the output will be Qn plus 1 is nothing but T XOR Qn. Okay, I hope I am correct. So this is the output. So whatever the memory you are going to provide, they are going to have XOR operation with the T input, and that will be your output. Okay, so because of the very less amount of time, I could not elaborate in great detail, but I just given you the expression. You could use it for solving assignment, or we could look in detail in the next session. Okay, I hope it is fine.
Okay, sir.
Okay, so is there anything, or should we wind it up?
No, sir.
Okay, great. Thank you very much, everyone. Thank you, Niranjan. Thank you, everyone, for joining. Have
Thank
a
you, sir.
nice night.
Good night,
Thank
sir.
you. Good night. Good night.